I don't know if you can see it, but the ratio of the screen has changed a little bit because I figured out what was wrong with my video yesterday. It had to do with the aspect ratio. Again, with this, I'm going to do essentially 4 examples. And then I'll let you work. Again, as I stated, I would have stated it earlier on, that stoichiometry is the key. It's kind of like the heart of what we do in chemistry. So it's important that we learn how to do this properly. Tomorrow we're going to do an experiment where we're going to use stoichiometry to predict the mass of a product that we're going to produce. And you're going to do stoichiometry for 5 different reactions to see and make a prediction which reaction is actually taking place. That'll be due Saturday at midnight, a classic Wednesday to Saturday at midnight. Not a formal report, fill in the blank, do a bunch of reactions, show me balanced chemical equations. So, take a picture of your stuff. I want to then on Thursday, before we continue on, I'm going to give you a little quiz. I'll write it down on the board. So to start on Thursday, I'm going to just write on the board a stoichiometry problem, and we'll do it kind of like when we did those little quizzes with the names and formulas. I'll just write out a stoichiometry problem, and you'll do it quickly. And I'll probably mark it myself because there's some part marks to be had, but just kind of a quick little quiz to force you to read over and know how to do stoichiometry. So it'll just be a quick 1-question type thing. And then we'll proceed, and like I said, Thursday, Friday will be done, Monday will be review, and Tuesday will be the test. Okay, so now we're going to do calculations involving mass. Yesterday, the calculations we did were called mole-mole calculations because we only used that bottom line where we moved from moles to moles. Today we're going to be either given some masses or determining masses, so we're going to have to add some steps. The first 2 examples I'm going to do are going to only involve 2 steps at a time, a mass calculation and a moles calculation. And then the last examples will involve all 3 steps where we've got to calculate moles and mass twice. All right? Gravimetric just really stands for weight. All right? Gravity means weight. It means really how heavy something is. So when we talk about gravimetric stoichiometry, it means we're measuring weight in the end. All right. Examples. And again, just like yesterday, when you're done writing out the question, try to write a balanced chemical equation. And then we will build our map. So this is a reaction we've seen many times. We're reacting some oxygen with some hydrogen to produce some water. So hopefully you can go ahead and write that one out, balance it up. I think we can balance this with a 0.5. Like I said, 0.5s do work in stoichiometry, but I'm going to try to avoid it just to kind of keep the mole ratios nice. And I'm hoping you've already kind of got that written down. We've seen this reaction many times, so you should be able to write down the chemical reaction that makes water from hydrogen and oxygen. You shouldn't have to wait for me. And it appears that you are. So, H2, O2, H2O, and I believe I'm going to need 2 of those and 2 of those. We could have did it with a 0.5 in there, but we'll leave it whole numbers in this case. So I'm going to draw the lines out one more time, but when I do the rest of the examples, I'm not going to draw lines. You'll have to imagine the lines. But I'm going to draw the lines out one more time, and in the top row, I put my grams. In the middle row, I put my conversion factors, or the number I'm going to use to turn it into moles. And then in the bottom row, I'm going to put my moles. So it says, find the mass of oxygen. So remember, this is my gram line, which means up here in the gram line and right below the O, I'm going to put question mark grams. Now, yesterday, as I walked around, I found that some people weren't being very picky on where to write this. This is not like writing a note. You're not blindly writing. The location of everything is super important because it's going to tell you how to calculate it. So the location is very important. 2.5 moles of hydrogen is how much I'm starting with. So in the mole line, I put my 2.5 moles under the hydrogen. All right? So now I have to get myself to grams ultimately. Well, there is no conversion factor, or there is no equation that allows me to go straight to grams, so we can't cut horizontally across this grid. In the mole line, we can only, sorry, not horizontally, diagonally. In the mole line, I can only go horizontally. So in the mole line, we go horizontally using that mole ratio, and that's what we practiced yesterday, so we'll do it again. So if you were writing a test yesterday and you didn't watch my video and you didn't do anything, which is unfortunate, this is what we did yesterday. You'll get a chance to see it. And now I'm going to move up. And I put an arrow up, usually, right through that conversion factor line. And normally, I don't write the number necessarily in there. You could, but I'm going to just put over here molar mass of O2, because that's what we need to, that's what the conversion factor is. So I'm going to need a molar mass of O2. Now when I solve problems, I know I've got to do the mole ratio first and then the molar mass. But as soon as I see that I need a molar mass, I write it off to the side, so I have it ready to go. So as soon as I see I need this molar mass, and it's over here on the right, I'm going to put O2, and I'm going to determine that molar mass. Periodic table, Russell, find the numbers, calculate. 16 times 2, 32.0 grams per mole. Okay? Now, I like to break the calculation into 3 parts. You'll notice we don't have a calculation here yet on the left where I'm going to turn grams into moles. That's going to be the last step. The last step is where we have 3 steps. So I like to kind of break my problem into kind of 3 areas where I've got my step on the left, I've got my mole ratio in the middle, and then I've got my step on the right. So since I'm starting with the mole ratio, I'm going to do that first. So just like yesterday, 2.5 moles represents the 2. So I put the coefficient underneath, equal to X moles, that's my question mark, represents the 1. All right? And I can bring that 1 to the other side. The math isn't that exciting. It's going to be 1 times 2.5 divided by 2. X is equal to 2.5 divided by 2, which is 1.75. Did I do that right in my head? 1.75? 1.25. 1.25 moles. All right? Now, it can be confusing because I have my X on the right and my 1.25 on the left. But that essentially means I have 1.25 moles right there. You can write that in if you want, but I solved for the question mark. Okay? Now I'm going to move up. I am going to abandon conversion factors. If you like conversion factors, you're going to take 1.25 moles and you're going to multiply it by the molar mass, whatever that conversion factor is. But I saw a lot of train wrecks on conversion factors on that last test. So, how do we convert moles to grams? We use the molar mass, and we use that triangle. Molar mass is equal to grams over moles. And unfortunately, I saw a large number of people that didn't know how to use this triangle. So let's review. If I want to determine mass, I cover the mass up, These two are beside each other. It's a multiplication. Mass is equal to the molar mass times the number of moles. And I apologize if this is painfully slow, but there are many that can benefit from this. I've determined the molar mass, 32.0 grams per mole times how many moles? 1.25. What mass of oxygen is required? Yep. Sorry? Is it 40? 40. Let's put a 0.0 on there because of 3 significant digits. And let's put an O2 because that's what we solved for. This is simple stuff if you practice it. The mole ratio calculation will always look the same. When we're dealing with grams, this will always look the same, okay? I could ask you for entities. Well, then I use the entities equation instead. Okay, let's do another one. Click. And again, the structure under the equation, we call that in the biz, in the science biz, we call that scaffolding to help you build your question. Some people hate scaffolding. They just do calculations everywhere. But if you need it, write it like that. Yep. Yep. No problem. So the scaffolding is to help you. If you know what you're doing here, you go ahead. This one's a little different in that I'm starting with a gram. It's my starting point. And I'm wanting to find moles. That's another two-step problem. Grams to moles, moles to moles. Then we'll do some three-step problems. Again, try to do the balanced chemical equation. Pencil is a great thing in case you mess it up. You can fix it. This is a synthesis reaction, so you're going to have to cross over charges to get the formula for your zinc sulfide. Now, in a moment, we're going to do the three-step problems. Some students say, oh, that's the hardest one. I'll only practice the three-step problem. But sometimes I only want 2 steps. You might say, why would you only want 2 steps? We like measuring grams. Why would we ever want to find moles? Remember, I talked about an experimental way to find the molar mass. Talked about that when we were doing our molecular formula calculation. This is one way to determine a molar mass, because we could use stoichiometry to figure out moles of something, and if I know the mass, I can figure out molar mass. So sometimes this is a useful thing. Does somebody have a balanced chemical equation? What do we got? Grace, what do you got? So zinc and sulfur, they're by themselves. When they become ions, they have the same charge. Therefore, you're saying it's ZNS, right? And therefore, that's balanced, isn't it? That's a super easy one. It's balanced. That literally is one atom of zinc getting together with one atom of sulfur, trading a couple of electrons and becoming ions. So the mole ratio is 1 to 1 to 1. That's nice. Building our map. 1 gram of zinc, 1.00 grams. So I write it in the grams location. Notice that it says that the other reactant, the sulfur, is in excess. We use that term often, stating that like we've got piles of sulfur, like all kinds of sulfur. So what this means is that the zinc is going to control the chemical reaction because I've got lots of sulfur, okay? I want to find moles of zinc sulfide. So down here a little bit, you're going to use your lines, but I'm going to be down here. I'm going to put question mark moles, number of moles of zinc sulfide. That's what I want. Again, there is no conversion factor that gets me diagonally across. but I can move down and figure out the moles of zinc. What conversion factor do we use to convert grams into moles? And my indoctrination is just so sad, isn't it? Molar mass. Molar mass. Molar mass. Again, in the past, I'd just write MM. But just to clarify it, because we're talking about zinc, I need the molar mass of zinc. Once I get those moles, I can go this way using the mole ratio coming from the balanced chemical equation. I break my question into two again. I'm not doing the third step yet. So this time I'll put my zinc over here and get the molar mass, get my triangle, get the appropriate equation, and run through the problem. What is a zinc? What's the mass of zinc? 65.4 grams per mole. 65.4 grams per mole. And again, to be honest, I would write that triangle out every time. I would have been too embarrassed to write the triangle because the triangle is a crutch. What I would do, like I said in the past, what I've done is I would go molar mass is equal to grams per mole, right? That's the unit, right? And right there, I imagine the triangle because I know how to imagine it, right? Oh, there it is. I'm going to multiply them. So what do I need to find here? In this case, I want moles. I'm going to have grams over molar mass, right? Again, for those of you who've memorized it, it's a good thing to do as well. Molar mass is mass over moles. So I want moles, and I need mass over molar mass. I've got 1.00 grams, 65.4 grams per mole. How many moles have I got? Again, ideally you're ahead of me. Yeah, what do you got? 0.015. Is there a zero after that? Or because I want 3 digits, and that 0 at the front doesn't count. It was a 2? Because, see, we want 3 digits and 3 digits. That first 0 just pushes it into smallness. It's a 0? It's a 2? It's a 2. So 152. 152 moles. Like I said, that first 0 just pushes it into smallness. So it doesn't count as a significant digit. It just makes it tinier. So we need the 3 digits that are not zeros. Again, you can write it into this spot if you really want. 0.152. It's going to transfer over. 0.0152 over 1 equals x over 1. That seems almost like a waste of time to write. If you didn't write that, I wouldn't be offended because I can see that it's a 1-to-1 ratio. That means x is 0.0152. That's a 0.0152. You could even just write that right across there because it's 1-to-1. I'm okay with that. Oh, I'm done the question. I was going to turn that into grams, but I don't have to on this one. Therefore, I have 0.0152 moles of zinc sulfide. All right? That is one thing I do want in an answer. You know, I say, don't write me a big fancy thing. Put a box around it. Tell me what the chemical is that you've calculated. Put that chemical formula as like part of the unit so that I can see what you've got. So again, that's another 2-stepper. All right? And you don't need to write this down. If I were doing this, sometimes I taught that in the previous lesson. 1 to 3 in part B are 2-stepper problems. But I'm going to just be assigning you the whole sheet anyway. Let's go ahead, and there's the answers. Not a big deal. Let's go ahead and do some 3-step problems. The reason I've got those questions down there is because in the past, like I said, at the end of the lesson of yesterday, I might have taught that 2-step one to give people a chance to work on a few more things, but because there were tests going on and stuff like that, I didn't proceed. Got them there. So this is technically what I would call a mass-to-mass problem. Starting with grams, turn it into moles, mole ratio to the other moles, using the other molar mass to get grams. So again, give it a shot. Find the mass of iron 3 oxide required. Therefore, it's a reactant. It's going to react with excess CO. It's going to produce iron, and the other product is CO2. A little bit convoluted there, but if you read it through carefully, you should be able to figure out your reactants and products. Again, I've given you the name of iron 3 oxide, so you're going to have to do some crossing over to determine a formula there. And then iron is iron. What do we have for the formulas? I don't need it balanced. You maybe haven't balanced yet. Does somebody have like formula of the reactant? Ready to roll? Yeah, what do you got? FeO. Now, if it's iron 3 oxide, I got to cross over some charges. Yeah, that's okay. Once you fix it up, just tell me what to put. Fe2O3 plus CO. And products, what do you got? Fe plus CO2. Excellent, good. Now we got to balance that one up. Now this is kind of a goofy one to balance. We can't do a 2-3 thing with the O's because there's O's in here. So this one's tricky. I don't know of any of our tactics that just work easily on this. When I find one like this and I don't have a tactic, I try to ask myself, what's happening in the chemical reaction? And so this carbon monoxide, well, what has to happen to it to become carbon dioxide? What has to happen to it? What? It gets an O. Where's it getting the O from? The Fe2O3. So then the question becomes, if it's got to get rid of 3 O's to become this, how many COs do I need in order to gather that up? How many carbon monoxides will be required in order to remove all of those O's? How many carbon monoxides? I need 3, because each one takes 1 with it, doesn't it? So that's kind of the way I balance this one. I think about what's that doing. I need 3 of those to gather up those O's so that they can become that. And now I just need to take care of the iron, all right? Again, we have a lot of people still just wanting to put subscripts there, but iron isn't one of the Hofbrinkel diatomic elements, so it's just Fe, and I need 2 of them there. Now I'm going to build my scaffolding. I want to produce 100 grams of iron, okay? The question is, what mass of that is required to do that? So in the grams line, I put my question mark grams. There is no conversion factor that turns grams into grams. The mole ratio can only turn moles into moles. That's why we can only go sideways in the mole line. So the only thing I can do is head down there to moles, head over here to moles, and then head back up there to grams. And I'm hoping it's becoming painfully clear. If I want to turn grams to moles, what do I need? A molar mass. I need the molar mass of iron. So I'll put my line here and I'll do it over here somewhere. And in this case, I'm going to need the molar mass of Fe2O3. And I'll do it over there somewhere. I don't have a lot of room on the left. It's going to be squishy. It's going to be a squishy calculation. And then I'm doing a mole ratio over here. Well, I'm going to start over here. I'm going to put a squiggly line over here. I'm going to do that calculation over there. Once I've got moles, I'm going to do the mole ratio. I'm going to put my line over here. Normally I would put it in the middle, but I need a little bit of room over there. You don't have to put those lines. I just like to see the compartments of where the calculations are. At this point, I'm hoping you're going ahead of me. Because even though I haven't done a 3-stepper, we've seen all the steps. Again, if you are an equation person, mass moles, put that up in the corner somewhere so you can grab the appropriate equations in order to do your calculation. And now I am purposefully moving slowly so that you go ahead and calculate before me. Okay, Aaron, 56.5? 50, is it a 56.5? 55.8. Not even close. 55. Where did I get 56.5? 55.8 grams per mole. I want to get moles. I need an M over MM. I got a 100 over 55.8. Somebody have that number? Again, I'm hoping you're ahead of me. You should be ahead of me. Carson, what do you got there? How many moles is that? 1.792. 1.792 moles. An extra digit to carry is good. There's only 3 there, but keeping an extra digit is a good play. Keep an extra digit and then round back. Yep. Yep. Nope. So, when we are converting to moles, we're just using iron. The 2 is only used in the mole ratio. If you bring a 2 in for the mass, and then use a 2 in the mole ratio, you've used it twice, and you will be off by a factor of 2. We only use the coefficients in the mole ratio, okay? So again, I'm going to set it up. This is now question mark. If you really want, you can write that into your chart, but I don't necessarily always do it. I know I'm in that position. I'm going to write 1.792 over 2 equals, I'm heading over here, x over 1. Again, I'm just putting the 2. That's where I'm using the 2. I'm going to bring the 1 to the other side. So x is going to be 1.792 divided by 2. I can't do that in my head. Carson, what do you got? 61. 8961 moles. 0.8961 moles. Heading up. I'm going to build my triangle. I should get a molar mass first, but I'll build it at this point. What do I want? I want grams. So I'm covering it up. Molar mass times moles. Mass equals molar mass times moles. I need a molar mass. Fe2O3. Squishy. 16 times 3. 58.5. Oops. 55.8 times 2. I'm catching up. Have we got a number? 159.6. 159.6 grams per mole, and 159.6 times 0.8961. And I don't know if you notice, whenever we do a calculation, we use the answer from the previous one. If you've got the answer button on your calculator, use it. It'll save you a little bit of time. So in this case, you're going to do 159.6 times answer equals. And what do we got? What did I do? Did I do a mistake? No, because I could have. I make mistakes all the time. What do you got? 143. 143 to 3 significant digits, which I like, grams of Fe2O3 required. Okay, we like it? Look good? Right. So there's a classic 3-step problem. And that's why I stated yesterday, if I give you a question like this, and I don't give you the balanced chemical equation, that's typically worth 3, all right? And then this is typically worth 2, so we're at 5. Another 2 there, usually setting it up and doing it. So there's 6, 7, and then there's 7, 8. These will be typically worth like 8. So if you can't do the balanced chemical equation, then people start to freak out. Oh, no, it's worth 8. Oh, no. But I know how to do stoichiometry. That's when you can put up your hand and I can give it to you, and then you can at least get 5 out of 8, right? I'll even cut a deal where you can write down the formulas that you know, and if you don't know the last, I'll just give that to you for a half. You see what I mean? And then you can even balance it yourself. So if there's one little thing that's missing and you know, oh no, I can't get it, the whole world's going to fall to pieces, right? Then you can do that, okay? All right, let's do one more. Yeah, let's do one more. Or do I have one more? I do. Oh, I got kilograms in there. Nice. That's why I put that in there, yes. We had some people struggling with the mighty kilo. I don't know who it was. There was. Who struggled with the kilo? Do I have a good enough memory to remember back where that? Oh, I haven't even handed them back yet. That's fun. This is fun. There was someone who really, oh, no. That's not who it was. What? Huh. I have 4 people in my mind who it could be. People that shouldn't have made that mistake. 1 of 4 people. I won't call them out. I'm videotaping this. It wasn't you. You don't come to mind. I don't believe. No, I don't think so. For some reason, I think it might be Madison, but I'm not sure. Either that or Dana in the other class, or one of the Jacksons. Because it was a mistake that those people don't normally make. That's why it stands out in my head. But I can't remember who it was. Don't worry, I'm sure it's all fine. It's all fine. It's not a big thing. Yeah, I know. Well, I always tell my friends, oh, I shouldn't be telling you this. And I say, don't. Because if you tell me, I am going to the very next person that I see and I'm telling that thing. You cannot keep that information inside of me. So don't tell me. If you really think don't, then don't do it. There's a reason for that, because, well, I like to tell stories. Find the number of magnesium chloride formula units. Oh, that's why I did this. Yes, produced when 60 kilograms of magnesium reacts with an excess of hydrochloric acid. So, what are my reactants here? What are the reactants? Magnesium and hydrochloric acid, Mg plus, oh, the dreaded hydrochloric acid. What's the formula for hydrochloric acid? Yep, just HCl. Again, the common error is to put, whoops, see, look at, I just was thinking what the common error is. The common error is to put the O3 on the back end, and that is chloric acid. So this is hydrochloric acid. The small little molecule with the big name, hydrochloric acid. MgCl2, and I believe we're getting some H2 with that. Single displacement. To balance it up, I think I need a 2 there. And I'm starting with 60 kilograms of magnesium. 60 kilograms, goes in the grams line. And this is really not a practical problem in any way. Who really cares about the number of formula units that are produced? Nobody really cares about that. Nobody cares about that. But it's a good thing to think about. Formula units, what do we call formula units? What group does that fall into? Yep, entities. I'm looking for entities. We'll talk about that in a second. Heading down here, we know it's a molar mass of magnesium. We're kind of seeing where that's heading. That's going to get me moles. Moles using the mole ratio. What do we call that special number that converts moles into entities? What is that? Yep. Avogadro's number. And A, and therefore I'm going to need that other triangle. And that's it. That's the only difference. we're going to find by the end of the course that there's going to be about 5 different ways or different things that I can do to go from moles to something else. You just have to pick the right one, depending on what we're looking for. We can get that NA equation in a bit. Again, hopefully you're going ahead of me. Don't just stand there and wait. Whoops, that's not an M, that's supposed to be an N. Don't just sit there and wait for me, because I know I can do it. You've got to see whether you can do it. Oh, I guess we got to do something with this kilo. I talked about that. Simplest thing to do with the kilo is to simply write the mass as 60 times 10 to the 3 grams. Just put a times 10 to the 3 on the back end. Your calculator can handle that. It doesn't have to be in special scientific notation. It's got a power of 10, but it doesn't have the decimal there. So what am I finding? Moles, M over MM, 60 times 10 to the 3 grams over, what is the molar mass, I think? 24.3? 24.3? You have a -3 there. That would be if it was a milligram, but this is a kilogram, okay? 24.3. How many moles? Yeah, Seth, what do you got? Doesn't make any difference. 2,469 moles. Doesn't matter. If you've got your even if you didn't have your calculator, if you had your calculator not in scientific notation, even putting that in gets you that number. If you had your calculator in scientific notation, your number is going to say 2.469 times 10 to the 3. That's fine. It's the same thing. All right? So there's my moles. 2,469 over 1 equals, oh, it's a 1-to-1 ratio. That's fun. X over 1. So it's the same number that's there. So that is also a 2,469. X equals 2,469 moles. Avogadro's number, again, you got to memorize it. I always think of it in terms of the units. If I check the back of the chart, it says entities per mole. So I will have N on the bottom, and I'll have entities on the top. Oops. I'll have a capital N on the top. I write it as entities, but it'd be a capital N on the top, the big number versus the little number. I want to get entities, so N entities is NA times the number of moles. 6.02 times 10 to the 23 times 2,469 equals. Yeah. Well, what do you? Go ahead. Go ahead there, Leah. Times 10 to the 27 entities. And we could round that to 3 significant digits, 1.49 times 10 to the 27 entities. Again, that's not functional for anybody. Who cares how many entities there are? It's just practice using another conversion factor in that spot. Okay. Yep. You thought it was going to disappear? Oh, it's not disappearing. So there's the rest of that worksheet. There's also some textbook questions. Again, lots of problems to do on this. I've got the answers on the worksheet. Practice makes perfect. If you can't get a balanced chemical equation, ask me or ask a neighbor to see if it's right, and work away. All right? And again, I say it over and over again, and I can see it when I'm marking the test. Practice, 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 practice. When you go to review for the test, do more practice. Just staring at questions and thinking about the steps does not put enough of it in your brain for you to do the steps. You've got to practice the steps. Yep. Yep. Oh, of course. Leave your phone to humor me. Makes me feel like I've got some control in this classroom at least. No, I'm just joking. No, leave the phone, but I'm joking about the control thing. You really don't need the phone in order to go to the bathroom. Yep. Anything else? What's that? Yeah, the bottom stuff's out of the, oh, it doesn't even say, oh no, sorry. So that's 4 to 10 on the worksheet, okay? And on Google Classroom, or I think at the bottom of the worksheet, there's also some textbook questions. All right? Calculator, right? Calculator. Oh, and my last 2 test writers are writing, so I hope to get that test back to you tomorrow. Oh, we've got a lab. We'll be across the way. Yeah, I can still hand that back tomorrow. Calculator. There you go. Yeah, so again, on the worksheet and as well, there's some textbook questions. The answers I put right on there. Does everybody have the information off of the slides? I can give this machine a break. Oh, and I can stop recording. I can stop recording.